good afternoon, good morning, or good evening, wherever you are in the world. I know we have people who signed up from all over. We are the Community for Rigor, for those of you who don't know us yet. We are an NIH, NINDS funded initiative to create a free online curriculum to help you learn, practice, and promote scientific rigor. So in other words, we're creating a network of resources to help you acquire those research skills that you so much need, but you are necessarily not taught to do good science. So anything from developing a good research question, reviewing the literature, creating reproducible code, how to randomize, how to do proper statistical analysis. Of course, we're also going to have a unit on the responsible use of large language models. So all of these steps that everyone assumes scientists should know, but sometimes nobody bothers to really teach you. And so you end up copying what you see at the lab. And those are not necessarily always the best practices. So we are here to give you a resource that you can just click online and go in there and learn the things that you should know as a good scientist. Konrad will be teaching you today our first released unit on confirmation bias. So very excited. We created this unit with a team at Harvard Medical School, some of whom have joined us at the webinar. So kudos to Richard Bourne, the neuroscience school, also the medical school at Harvard. And so without further ado, I'll introduce you to our PI and fearless leader, Konrad Kording. Most of you know who he is. He's a neuroscience professor of integrated knowledge at UPenn, which means he teaches at both the engineering and the medical school at UPenn. So again, without further ado, thank you so much, Zach, for the plug there to join our mailing list. I'll give you Konrad Kording. Thank you.
Wonderful. Great to see you all here. I will be unable to see the chat while I present. So if there are any comments, I would ask my co-panelists here to please let me know about them. Without further ado, let's jump right in. Confirmation bias, the original error. And we will start this with an interactive activity. One of the things I really love about C4R is that we have all these interactive activities. So let's start with one of them. This is an activity where you will try and deduce the number rule. This you can put in 3 numbers and it will tell you if it's true, if it's like according to the hypothesis or not. So let's do some hypothesis testing. Let's all be the scientists. So the activity is enter numbers to guess a secret rule. You'll see a screen that looks like this, where you have a sequence, say 2, 4, 6, and then it says, does it match the number rule on the right-hand side? And then below that, you can put in your own, no, and 2, 4, 6 is true. And then you can put in your own set of numbers, maybe 3, 5, 9, or maybe 2, 4, 8, what do I know? And then you can test your hypothesis. And then you can do that for a while until you come up with, like in this case, 3 minus 6, 99, false. And then you can keep doing that. And you'll do that until you feel like you've figured out what the rule is. And then there's a submit your hypothesis button where you can kind of say, this is, I believe, 3 numbers and they must all be prime numbers and in the set of Konrad's favorite 20 numbers or something like that. And so let's get started for that. So you can here get yourself to this screen. And I want to I will give all of you now like about 5 minutes or so. I'll ask regularly in chat if you feel like you already have your rule, and you're gonna find out what that rule is. I should also say everyone is gonna get a different rule, so or at least there's a whole bunch of them. So you don't need to collaborate on this for the time being.
Konrad, can you put the link on the chat very quickly, please?
Yes,
Thank you.
the link on the chat. Hold on, like it's already, Zach just put it here, no?
Yes, thank you.
Great. So what you see is the link there. Um, it's the HMS Watson 246. Let me like repeat that. Audrey, go ahead. Okay, let me also see if I can find the rule while you all do it. It's too much fun. I've played this many times, and okay, okay, let's see. Okay, people start having their rule. Um, I thought I had it, and now I don't have it. It's not just that they have to go up now, like Okay, I think we should wrap this up here. Who is anyone still working on their rule? Okay, it sounds like everyone's finished, so let's go back to presenting. Okay, so what has just happened? So what we always find when we do these things, that there's a large number of people in the room that believe that they know their role, and then in the end, the rule is different. I unfortunately we don't have that interactivity here, although you can say on chat if the rule surprised you and it wasn't what you were expecting. So what has happened in this case? Um, did you falsify your research? Now, how did this activity go for you? Were there moments when you realized you needed a new strategy? And I want you to just like sit for a moment here and reflect on that process. How did you choose the numbers you put in? What were you trying to do with the numbers that you put in? And I'm gonna like give you like a 1 minute or so, 2 minutes maybe, to just think through what the logic was of what you just did there.
Believe we had a hand up somewhere. I think
Yeah.
on it.
Oh, but the hand's down now. Yeah, if anyone wants to say something in public, just say it in chat and we can advance you so that you can be panelist and say something. Um, Good. So when I started these things, when I started working with this unit, I found myself that I get like a hypothesis of what's true, and then I tried lots of things that were like basically looking for that same truth. And so what have researchers found about bias? Here's an experiment. So no, like, and so like it very much seems that what we usually do is just like we try and find evidence for what we were looking for. And in fact, we have a histogram somewhere where we have all our participants. And in that histogram, what you see is that the vast majority of queries are kind of in line with the hypothesis that people already have. And they very, very rarely participants here. Very rarely do the participants try something else at that given point of time. They're not trying to like, oh, let's see, my hypothesis could be wrong in this way, and my hypothesis could be wrong in that way, and so on and so forth. Instead, what they usually do is they have a hypothesis and kind of keep going at it. And unfortunately, arguably, science is a little bit like that. So what have researchers found about this confirmation bias? Here's an experiment that shows how context inserts bias that interferes with expertise. Let's say you have 5 fingerprints experts that agreed to study and examine prints they had previously identified as matches. Um, the catch, this time the experts were told the prints were erroneously matched. Okay, so here we have 2 fingerprints. To me, they look very similar. I don't know what like the experts think here. And the experts were instructed to ignore the context information and given unlimited time to examine the prints. This is a fun experiment by Drawer et al. From 2006. We are swayed by the misleading context, even if we know better. 4 out of 5 experts in that case contradicted their own previous identification, incorrectly assessed the prints were not a match. So that means that, like, if I tell an expert, or if someone tells me being an expert in computational neuroscience, that something is true, I will probably, just like these fingerprint experts, be very much biased towards believing what the rest of the world tells us to be true already. And yes, in fact, like I was just going to read this. So Ronit Kapoor said, yes, I raised my hand to share that I was trying to repeat the true cases, but I overthought the rule. Uh, So yes, like we all come with our bias to what we want to see. And of course, in science, that's problematic because like if we already believe that we have an idea on what we want to see, and most scientists, myself included, kind of like at least have that when we start an experiment, that will of course affect the results that we will find. Now, and only one expert here maintained the original match judgments. Experts are vulnerable to irrelevant and misleading contextual information. Um, we discount information that undermines our past judgments. We fall in love with our own hypothesis. I fall in love with our own hypothesis. In a betting scenario, participants significantly increase their bets when their partner agreed with them. And they only slightly decreased their wages, however, when their partners disagreed. So if you agree with me, if the field agrees on something, everyone's like gung ho, like yeah, that's the way things are. If someone is the naysayer, that has surprisingly little influence. And unfortunately, I'm also often the naysayer. As you can see, we tend to confirm our hypotheses, both in the experiment that we did here, like the little number rule guessing game, as well as when we do science. This impairs our research. This tendency is a cognitive bias called confirmation bias, and this is what this unit is about. Lesson 1, our biased brains. Confirmation bias, people's tendency to process information by looking for or interpreting information that is consistent with their existing beliefs. By distorting how we think, confirmation bias skews our ability to conceive, test, and evaluate scientific hypotheses, and there's a wonderful paper by Kahneman and Tversky about that. In this unit, confirmation bias also covers two related cognitive biases. The first one is expectation bias and observer bias, now where we expect something. And here's an example of the expectation bias. Expectation can produce changes. In the 1960s, Rosenthal and Vogt asked students to train two breeds of rats to solve mazes. There were maze bright and maze dull rats. The rats were actually genetically identical. Like this is a study where we want to find out how biases affect the scientists. So they're exactly identical from the same background, these mice. And students' expectation affected training and created performance differences by the end of the study. So if they want to see it, they will see it. Also, this is expectation bias, also known as experimental bias. It is the tendency for researcher expectations to influence subject and the outcomes. Experimenters' expectations can produce an actual measurable difference in performance. And expectations can affect data collection. In a more recent study, students were asked to rate the sociability of two breeds of pigs. I love pigs. I recently found that there are coffee shops where you can cuddle little cute like pigs. And since then, I really have a deep love for pigs. Video recordings of normals versus highly social breeding values, SBV, normal versus SBV plus pigs. The labels were identical, but pigs labels SBV plus were rated as more social. Students did not interact with the pigs, so differences resulted only from varying human perceptions. So if I tell you these are sociable pigs, you'll be like, oh, look like how cuddly and like sociable they are. But I tell you these are like really like just for themselves, out for themselves pigs, you will tend to see them as if they're just out for themselves. This is the observer bias. This can look like this. Tendency for researcher expectations to influence their perceptions during a study, thus affecting outcomes. Expectations of data collectors can cause perceivable differences that are not actually there. These biases impede our rigorous science and impair our ability to design informative, objective experiments and interpret experimental results impartially. We can manage this inclination towards confirmation bias. And this is kind of like the thing where like the first thing is like super useful for us to be aware of these biases. And the second one is we need skills so that we can minimize them and we can manage this inclination towards confirmation bias. Since we know confirmation bias distorts the results we have, how should we frame and ask questions, seek out information, collect observations, and make sense of data? We can mitigate the bias by, for example, building habits to formulate better hypotheses. Now, if we acknowledge that we have biases, we can say, okay, let's see, given that, what would be meaningful alternative hypotheses here? We can seek out information with that knowledge, which is design experiments to rigorously test and compare hypotheses, can collect observations, use appropriate experimental methods to reduce errors. And we can place results correctly on the exploratory confirmatory axis. Now, like, it's important for me to know, oh, I had this idea and I was looking at it and I just saw these things versus I had a hypothesis that was clean that I was feeling positive about and another hypothesis. And then I did an experiment where I can really be sure that this confirms my prior belief that I have. Let's learn how we address bias through a process called masking. And masking is something that I personally started really caring about much, much later in my life. Now, like I've done behavioral experiments all the time. In the fact that if I have people and I assign people from different groups, people into different groups, I've never been like really formal about that. And now I feel bad about some things in that area. So lesson 2, no, like the lesson 1, like the goal of lesson 1 was like that you come out of it and are like, oh, wow, like me too can be influenced by expectation bias with the activity. And also like that there's a broader literature that kind of says, yeah, like expectation biases are a thing and they will affect everyone. And now we get to like, given that we acknowledge that, what are the procedures that we can do to kind of make it be less bad? And the first one is mitigating bias through masking. Experiment design and execution involve many decisions. Now, like, how do I show you some stimulus? How do I rate how active the rats are? How do I rate how social the pigs are? These decision points can be a place where confirmation bias affects our work. Let's look at some choices in a simplified experiment. Example, you are testing a new Parkinson's drug. The hypothesis is that treated mice are more active. So here's the person running the experiment, the preparer of the experiment. We're going to take syringes containing the containing the Parkinson's drug, and we're going to take control syringes. They're just filled with saline. And then you take the first 3 mice that you get out of the cage and you give them the Parkinson's drug. Oh yeah, and by the way, if I say 3 mice, of course we need far more mice. This is just to like keep the examples nice so that you see it all on the screen. But that's not the focus here. Like imagine it's a larger number and every mouse we plot here stands for a bunch of them. And so then I take the first 3 out of the cage, inject them with the treatment, with the drug. Then I take the next 3 out of them and inject them with the control drug. Of course, I know which mice I took out of it. Now, you're aware which mice look more active before the experiment. You may assign them to treatment. Now, like, what if I'm like, okay, I'm going to give that treatment to the first few mice that I pull out, and I'm going to pull out the mice that are active because I'm like, yeah, this mice look like maybe good. We want the treatment to work, no? Like there's a possibility. So then the data collector, no, like you collect the data. You're like, okay, let's rate how they are. You might say mouse 1, 2, 3 are all more active, and only mouse 6 is more active on the right-hand side. But look here, you expect the treated mice to do better. And so when you rate them, you're like, yeah, you know what, like, that looks pretty active. And I know that I took them out. Now, I'm the person who collects the data, and I'm also the person who injected them in the first place. So I know who's in the treatment arm. And you expect the treated mice, so you may view them as more active. And then you do the data analysis. Now you're like, oh, yeah, look, this isn't significant. Let me like throw away this one mouse, which is an outlier anyways. Like, who cares about outliers? And after outlier collection, the treatment group responds well relative to the control group, and it's better p smaller than 0.05. Now you see there's like 3 places where bias comes in. We choose who to inject, we rate them how they are, and then on the data analysis side, we choose if we going to throw away the data or not. In this case, we chose to throw away one of the mice. Now, so each of them is pragmatic. Each of them is a place where our biases enters our experiments. Now, do you feel the outlier needs to be rejected? Thankfully, your results were statistically significant. So what's wrong about this? Unfortunately, we don't have like a good mechanism to discuss with one another. We're going to figure that out for future webinars. But basically, if we see these things on this slide here, like these different stages, the administrating, the collecting data, and the analyzing the data, like that's all the things we do. Like when I run experiments, like kind of like every one of these are key for my task, and every one of them is just wide open to like experiment to biases. So I think that we really want to be careful about like minimizing this. Cool. Then let's keep going. So by not withholding information at important steps, all these choices introduced biases. But imagine I hadn't known it. Imagine I had collaborated with Zach and Zach would have like kept me in the dark and I would never have found out which mouse is with them. What should we do instead? No, mask our study. Masking is the process by which information that has the potential to influence study results is withheld from one or more parties involved in the research study. Masking and blinding are terms that describe the same practice. We use masking due to ableist connotations of associating blindness with being unaware of information. And can masking really have an impact on experiments? Let's look at some examples. Now, failing to mask significantly inflates effect sizes. So in that study, they took cases where there was no masking and found that they find significantly bigger effects. When treatment allocation is masked, measured efficacy of a drug NXY059 drops from an average of 54 to 25%. So not only does it bias things, but it can bias things massively. Like a drug that makes 50% of people better is much more meaningful than a drug that does that only to 1 in 4 people. When treatment allocation, here, in a meta-analysis of 290 animal research studies, the odds of reporting a positive result were 5.2% greater when neither masking nor randomization was used. 5 times greater, massive effect. If I read new clinical studies that are not very, very carefully studied, I see signs of that everywhere. In other words, failing to mask adds a bias that can increase effect size somewhere between 0.3 and 1 standard deviation. Key idea here to interpret that is like the average drug that people take out has an effect size in terms of standard deviation that is well smaller than 1. There's very few studies that have an effect of 1. So this influence of not masking is as big as the influence of the good drugs that we currently test. So it's a really massive, massive influence. Now, very large clinical trials are usually very, very careful about that, but most of us scientists aren't nearly as careful. But the reason why the big studies are so careful about it is because that experience of drugs not actually working in reality is very actively felt in medicine. So here we have another activity. I want you to use these power curves to explore how the probability of detecting an effect is affected by masking failures. And Zach will again share the link for that. And now this is an animation. This is an interactive that very nicely highlights standard statistics that you've all seen there. And we have 2 sliders here. The first one is sample size. And we can change, this is with a sample of 5 mice or humans, and you can change the number of subjects that you have here. And here we have the amount of bias that we have. And on the x-axis, you have the true effect size. Now, 0 means there's no effect at all. -2 standard deviation means that the effect makes you 2 standard deviations worse. 2 sigma means that the treatment makes you 2 standard deviations larger. And then we have the bias here. And I want you to like think a little bit and play with this for just like 3 minutes. I'll be back at 12:34. And I want to ask you how much the probability of seeing an effect, if there's no effect at all, is influenced by the bias and the sample size. And if you feel you understand the sample size bias probability of false positive effect based on this, do let me know in the chat, which I'll be looking at now. Okay, I leave you 1 more minute with this visualization. Okay, so let's explain what's going on here. So keep in mind that standard statistics that we use controls the false positive rate to be 5%. Not like here you can see 100%, 10% here, 0%. And you can see it crosses. So by definition, the test that we use will have 5% probability of having a false positive. Now, what I want you to see is what happens if I change the sample size. Do you see what's happening here? The false positive rate stays at exactly 0.5. No, like if I have 100 subjects of 5 subjects, it's calibrated so that if there's no effect, I always have 5% probability of seeing this. Now, let's say we now add bias, even a weak bias, not like 10% bias. Now it's no longer calibrated. Look, like now it makes 10% errors, 10% false positives, even if there's no effect. Now imagine we now increase the number of subjects a lot. In this case, we have a pretty small bias, not like that's a fifth of a standard deviation. That's much less than you'd get if you like judge any behavior and you know what's going on here. But you can see the larger the number, the larger this gap. All of a sudden, a very small gap makes a huge difference. So basically, if you have a 0.2 bias, which is tiny, and you have 100 subjects, you're basically very, very likely to see an effect, even if there's none. And that's, of course, it breaks the logic. Now, like the logic of statistics is that I'm only using this button, how many items I record. And then it's totally fine. But as soon as I add bias to that, I have destroyed the logic of statistics. There's nothing in statistics that prevents me from this. And like for 100 subjects, if I have a bias of 0.5, half a standard deviation, still not a huge bias. I will basically see false positives 100% of the time. So so the logic of this is that really I think we're often deceiving ourselves by and believe that like, oh, there's a small bias, it probably won't have an effect. Like, no, like as soon as we have relatively large numbers of subjects, even tiny biases make it very, very likely that we're going to deceive ourselves. And statistics is great at avoiding us deceiving ourselves from having too few subjects. But statistics by default has nothing that protects us from introducing biases. What that just means is we need to be like super, super clean when it comes to like avoiding bias in our workflow. Now, even if you throw away 1 in 10 of your subjects, like based in a biased way. If you throw away a tiny number of your subjects in a biased way, you still all of a sudden go from a situation where you should have very low probability of seeing an effect if there's nothing, to basically being guaranteed to see an effect if there's nothing. And look, we have so many degrees of freedom in data analysis. We have so many degrees of freedom in experimental design, so many of them in like judgments of if there's subjective judgments involved. It just means that we really must blind, we must mask. Wonderful, great. Let's go back to the presentation. So these intuitions about how bias and number of subjects really like affect experiments, I didn't have an intuition for that. No, and like, look, I admit it in like some of my earlier papers. I was like, yeah, it's like, look, this subject is an outlier. It's probably fine to exclude that subject. I didn't know better. Like and I never got an education in kind of rigorous design. There was not something that like they taught in any courses at university. But now that I kind of like that I'm in tune and that I've kind of seen with all these activities how big like seemingly tiny influences are, I'm very concerned about lots of things. Okay, we'll be skipping over that because we don't have a good mechanism of like discussing with one another. But what I want you to each like think about a minute or so is like these kinds of biases that we talked about. Now that you've seen how big the influence is, that even small biases have on outcomes. Think about your own workflows. It's kind of most workflows have options for biases. No, and I give you some examples. No? A lot of people do experiments before they choose what their hypothesis is. A lot of people do that. Guess what? Like if you do the experiment first and then decide how you analyze things, there's like a lot of ways how you can like shift it a little bit. As soon as you allow yourself to shift things, there's no way of preventing you from subconsciously shifting it a little bit. No, like this, it's kind of like this just shows like kind of the severity of like small biases, tiny biases for the kind of numbers of subjects we have at the moment will translate into guaranteed false positives. And a lot of the literature may be seeing these effects. How does masking combat confirmation bias? Now, let's be clear about it. Just as confirmation bias distorts how we frame and ask questions, seek out information, collect observations, make sense of data, it also exposes research to risks, such as raters make judgments when collecting data, data analysts make modeling choices. We can use masking to mitigate bias by withholding details that affect direct observation and judgment, providing de-identified coded data to prevent biased analysis. Think back to our example. How do you actually do the masking? Example, you're testing a new Parkinson's drug. Hypothesis, treated mice are more active. Same thing. You prepare the syringes. Now I go and like put the Parkinson's disease into some of the syringes, the cell line into others. And then I ask a colleague, in this case, Zach, like, um, hey Zach, here's like the syringes. Can you give them to mice? And he would then randomly give that to a subset of them. Your colleague ideally doesn't know which mice are more or less active. No, they are randomly assigned mice to each group. It's going to be every mouse has a number, and we're going to just use a computer program to randomly select half of them. And then you do the data collection. I'm the same person as before. It's a lot of work. I wouldn't like make Zach do it. That wouldn't be fair. And so we have like, I look at it and I'm like, mouse one and three are maybe more active, and mouse six is maybe more active. But of course, I don't know which one is which. And therefore, there cannot be a bias. It's like logically impossible for me to have a bias because I have no idea which of my syringes ended up in which mouse. In fact, only Zach knows that because he has a list of which mouse he injected with which number of syringe. And since you don't know the group assignments, the observations will be more objective. In fact, the class label, who got treated, you won't even know. And then you have an analyst, and ideally a new colleague, because otherwise, if Zach knows who got what, then he could like be biased by that. So you find someone else, your colleague carefully compares the two groups and find that there's no statistical significant difference. Now, like we said, like doing outlier rejection could be biased. Well, like if someone else does it and they don't know which is which, they will like use outlier rejection in an unbiased way. Now they'll be like, like this mouse really is different from all other mice. And therefore, we really probably shouldn't use that mouse because it's like fundamentally different. And then it's their call. And because it's their call, they don't know it. And that way, you can, since you now followed the thoughtful experimental designs, you have results you can trust. That goes both ways. Now, like it massively increases the probability that your experiments will say, well, actually, this drug doesn't do anything. But it also, when you do, it produces a situation where you can be really positive about it. And my lab now uses like those kinds of procedures, and it really encourages us to like we found one thing recently that was really interesting. It really encourages us to like go like, okay, like we trust this. Let's see if we can build a company around that. So not like because like we can now trust our own results in a way that we really couldn't otherwise. So how did taking steps to master study impact the results? Again, we don't have a great mechanism for thinking about it. But what I want all of you to think is in the framework in which you do experiments. So like spend like 3 minutes now and ask yourself, what are the aspects of your existing workflows that you could actually mask? Okay, great. Why don't we continue here? So, who and what must be masked? Now, like, mask anyone with a possible influence on the outcome of the experiment. Now, in many cases, it can be a simple procedure. Now, like someone like just randomizes a piece that you need to know to be biased. There's single masking participants for human studies and animal care staff for animal studies where they don't know it. There's double mask where you mask the experimentalist and the clinician. Triple mask, data collectors and data analysis should also be masked. And like you can say, in the end, you'd like everyone who's involved to be meaningfully masked. What gets masked? Well, mask the samples. So people conducting the experiments, administering drugs and placebos, and people assessing the outcome, making observations and recording data are not aware of which treatment is being administered and which group a given sample belongs to. Also called allocation concealment. For example, using sealed envelopes until after participant has been irrevocably entered into a trial. A fun example that we had is we were doing experiments where people were lifting coffee cups. I have something going for coffee. And we wanted to make the coffee cup heavier and less heavy. The way we did it is we printed a list of in which trial the cup was going to be heavy versus not heavy. The way we did it is like we literally had a postdoc like fill it with water from behind. I emptied it with water. And the postdoc had like a long list printed out of in which trial it was going to be heavy versus not heavy. The experimentalist was behind the subject, which was wearing headphones, so they couldn't hear the water flow. And this way we could like really be sure that the subject doesn't know in which trials that the cup would be heavier. And in any case, masking the samples, allocation concealment works to prevent selection bias by using a mechanism to prevent foreknowledge of upcoming assignments. As you can see, masking is a complex process even when seemingly simple. What should you do if you have limited resources or tools? Randomization. Use a random number generator to set treatment allocation order, reduces selection bias. Now, if you like randomly assign things, you first number the mice, and then you look at the list of who gets which injection. Already you get like the assignment bias, get rid of the assignment bias. Strategic masking. Use coded labels to keep key support staff unaware of group assignment. Now, like, let's say we do need to do that randomized injection of drugs. We can totally have like one person like basically take every syringe, just give it the numbers, and then somewhere on the computer sits this table of which syringe contained which drugs, and we get rid of, and everyone can now see the syringe. It just says number 13, but no one knows, is this the drug or is this not the drug? There's problems, of course, but like we can't talk about all of them. Robust measurement. Now, design studies with measurements that resist subjective influence. You want to know how active the mouse is? Well, maybe using code that uses like post tracking. There's like Deep Lab Cat is a cool project for that, or Sleep by Pereira. Having like automated methods like takes out the rater's biases there, no, because it's just code that you run who doesn't care who's in which group, and you would never tell it to that. Robust measurements, pre-registration safeguards, no, pre-register study protocols, and get peers to check your masking and monitoring procedures. No, like, can make the plan before and then do that. You can also make your data analysis pipeline ahead of time and then do that. This is something that we usually do now. Like it's a relatively easy thing. You're like, okay, I'm going to take one mouse only so that I know what format my thing is, and then I write the whole data analysis pipeline, and then I register that. Now I have no more degrees of freedom because I just like uploaded it, registered it in the data from that one animal we'll throw away. Next, let's examine some risks to unmasking. Lesson 3. Oh, wow, I'm slower than I thought. How good is your mask? I will have to get through here in 10 minutes, and I will get through it. You've masked your study, or have you? Masking may not be fully effective depending on the circumstances. What if a psychoactive treatment causes an obviously good time and patients notice changes in perception and behavior? And like classical prom, like if you give people psilocybin or something like that, they will like definitely know that they're not in the saline group. No, like they will be tripping and they will know that they are. It's very hard to control in those cases. A treatment causes inflammation at the site of injection, whereas the control doesn't. Now, very hard to like avoid that. Then the team will know about it. Animal strains have differences that are unrelated to the behavior of interest. Now, like maybe your control mice are transgenic and have like a different fur colors. Or the funk of the raven. Even when you have taken steps to mask in experiments, there are unmasking risks. Certain clues can accidentally unmask an experiment and come from sources such as differing side effects, healing rates, caretaker behavior, equipment, or procedure discrepancies. Let's explore where in an experiment unmasking might occur. Here we have another activity. Zach will be sharing the link for that. How are you completing this activity as a group? Here's the link. Copy a link, and I think now I can share it with everyone myself. Let me try that. There it is. Wow, I learned how to operate this activity better. We should have randomized it so that we make sure that if it's actually learning instead of just someone telling me. So we start the activity. And this is basically an activity to help you think about how math may fail. And I'll give you 5 minutes for that activity. Okay, I'm gonna give you 1 more minute. Okay, let's continue here. Um, so how do we manage these challenges that math can fail? How do lessons learned from this case study apply to other areas of research where similar biases could occur? We will also be like not having that discussion here. We'll probably experiment with breakout rooms next time. I think it's a fun idea. We are getting started. Now, like for everyone, this is the first time that we publicly put our materials out like that. We are still experimenting on how to best do that. It's yeah. In any case, but should we also formally assess whether participants, research administrators have been unmasked? And like, how should we do that? Turns out assessing if masking has been done or done correctly can be complicated or mislabeling. For example, in my own motor control research, I often found that subjects in their behavior clearly know something, but if I ask them if they know something, they have no idea that that's happening. So there is no consensus on how the efficacy of masking should be assessed. It's a nice paper by Bonn here. In fact, sometimes explicitly assessing the effectiveness of masking inserts bias when questioning study participants. Strategies to mitigate and test for accidental unmasking broadly have been discussed here. Use placebo controls to prevent treatment effects from revealing information. Provide clear, neutral instructions to minimize expectation bias. Review past masking procedures to improve future designs. Report participant expectations and unmasking instances for accurate result interpretation. Like we just want to be aware of the risk of unmasking. We always want to look for evidence of that. Differential side effects, e.g. noticeable nausea or drowsiness or other treatment cues can lead to unmasking. Placebo controls are never quite perfect. What if an experiment absolutely cannot be masked? I told you about the psilocybin studies, not ever going to be unmasked. Sometimes masking is nearly impossible, as in psychedelic drug trials. Even so, bias can be reduced by measuring and accounting for pre-trial treatment expectations. Report it. Report all the things that could be relevant for that. Strategies for reporting studies that cannot be masked. State masking was incomplete and describe why. For example, for psychoactive effects. Summarize participant guesses, ideally using indices like the Bang-James blinding index, and include confidence ratings for the guesses. Describe key trial instructions, advertising, content details that could shape perceptions. Explain the potential biases, treatment effect estimates, and note any analytic strategies like conditioning on participants' beliefs to adjust for these biases. Present baseline and post-intervention expectancy using standardized tools like the Stanford Expectation of Treatment Scale to quantify how participant beliefs may bias outcomes. Your research is on the road to uncovering reality beyond the bias. Keep questioning and testing, challenging assumptions. Scan the code and give us feedback. For anyone who's here with the phone, otherwise, I'll ask Zach if he can also share the link to this. Okay, with that, we come to the end. Better science every day. This was the confirmation bias unit. I want to thank all of you for being here with us and helping us basically test the first version of this. I wanted to briefly talk about what we are hoping here. Our hope is that you folks and everyone else seeing these will start like running units like that for your groups, for your friends, kind of like so that people become more aware of the biases that we have. I think we're in a literature where there's a lot of bias everywhere. I think we come from a place where we weren't nearly as aware of biases as we are now in science. Um, and I'm not sure if you realize that, but normally I totally freestyle slides, so I just like explain my story on it. Mostly what I did in this presentation is I just read what's on the slides. It's all designed so that everything that's really necessary is on the slides. The idea is we want to make it very easy for people to say like, hey, let me bring my friends together and tell them about confirmation bias or whatever else. Now we will put out other units. This is the first unit we're putting out, confirmation bias. There will be things, okay, let's talk about like how large language models like ChatGPT can like produce problematic outputs. And like there's this kind of like all kinds of like, there's many different aspects of scientific rigor. Now, I hope this was also like somewhat fun for you. It sure was for me. And I want to thank all of you for participating.